Okay, so welcome to the webinar on differentiation 2. So I have 6 questions prepared for you today. Hopefully we'll get through them reasonably quickly. I have to say that I have already done at least one webinar on this topic. If you don't know where to find those webinars, you go to our website, and on our website you find webinars. You click webinars, and all the webinars from last year are here. So year 13 webinars, you click all year 13 webinars, and circular motion, complex numbers, circular motion, differentiation, differentiation 2. So webinar 09 is differentiation. So please watch that, because today is a different one. Okay, consider the equation. Find the derivative of y with respect to x in terms of x and y. So this is an example where you need to differentiate. So we know the rules of differentiation, and the rules of differentiation are that if you have the product rule, uv is equal to u strife v plus uv strife. Okay, so and we know that if you have g of x, like f of g of x, and you want to differentiate that with respect to x, is the derivative of f with respect to g multiplied by the derivative of g with respect to x. So what do we do? So this is the product rule and the chain rule. So we differentiate both sides. We differentiate that, and we differentiate that. So differentiating the left-hand side, well, this is easy. This is 6x minus. Now here we need to use the product rule. So I leave the 2 out. The 2 doesn't make any difference. So I have xy is going to be x prime y plus xy prime plus, now for y cubed, I need to use the chain rule. So it's going to be 3y squared multiplied by y prime. How well do you understand what I just did on a scale of 0 to 10, please? How well do you understand on a scale of 0 to 10? Is there anyone confused why I have y prime here? Okay. That is a valid question, Matthew. Yes. How do I do y cubed? So y cubed prime is the same as d of dx on y cubed. We are differentiating that. Okay. What I'm going to do here, I'm going to use the chain rule, because I can't differentiate that with respect to x because there's no x. So what do? I differentiate it with respect to y. I do this by multiplying y cubed. I multiply the whole thing by dx over dx. And dx over dx, understandably, that is y, 1. So you can multiply by 1. And now you switch those around, and it becomes d on dx of y. What? Sorry. D over dx of y cubed. I multiplied by dy on dy. Sorry, I messed it up. So this is 1. I multiplied by 1. So far is cool, Matthew? Okay. Now I switch dy and dx, so it becomes d over dy of y cubed on dy dx. So what I did, I switched those around. And now I have d on dy of y cubed times dy on dx. And this becomes d on, I can easily calculate that. This is 3y squared. And dy on dx, well, that's y prime. Right? Does that make more sense? Do you understand now? Don't worry, I'm not singling you out. It's just I had 20 replies and 30 people didn't say anything. So 30 people have just were probably in the same position as you are. Always ask. If you don't understand something, always ask, because chances are that 30 other people don't know it, but they're too shy to ask. Derivative of 8 is 0. Okay, so we look at this, and now we expand the brackets. So we have 6x minus 2xy minus 2xy prime. Well, x prime is 1, so we can delete that. We don't need it. 2y. And now we do plus 3y squared y prime equals 0. We take everything containing one y prime to the, let's say, to the right-hand side. So it's going to be 6x minus 2y equals 2xy prime minus 3y squared y prime. So take the 3 out. 3x minus y equals y prime 2x minus 3y squared. So y prime is 2 multiplied by 3x minus y over 2x minus 3y squared, and this is the answer. So I just found the derivative in terms of x and y. This is called implicit differentiation. Implicit differentiation. Implicit differentiation. We use implicit differentiation when we can't make y the subject. It's close to impossible to make y the subject here. If you look at it carefully, there's no way you can do y equals something. And this is when we use implicit differentiation. Cool. Moving on. Question 2. Find the equation of the tangents to the ellipse 4x squared plus 9y squared equals 36. So it is an ellipse. How to draw this ellipse? I reached I reached for the for Desmos, but no, I'm not going to use Desmos. I'm going to draw the ellipse by myself. So this is x and this is y. So I just ask myself, what happens? What if x equals 0? Well, if x equals 0, then 9y squared equals 36. So y squared is equal to 4. So y is plus or minus 2. So if x is 0, y is 2 or minus 2. Okay. Then I ask myself, what if y equals 0? What if y equals 0? Well, then 4x squared equals 36. So x is plus or minus 3. 1, 2, 3. 3 and 3. So you can now see that this is, in fact, it is an ellipse. Another hint that it is an ellipse, well, because you know the equation of a circle, y squared equals r squared. So it does make sense that this is some sort of a circle-ish thingy-majig. So the fact that it is an ellipse makes perfect sense. Here's the ellipse. And just to be on the safe side, go to Desmos. And is it 4x squared plus 9y squared equals 36? Haha, here it is. A beautiful ellipse. Okay. Find the equation of the tangents at the points where x is 2. So x is 2. So there are 2 points where x is 2. So we can find these points. So it's 2, 2. Now, you need to find y. Well, you just plug that in. You plug in 2. So 4 times 2 squared, 16. 36 minus 16, that's 20. 20 divided by 9. So y is square root of 20 divided by 9. 2 root 5 divided by 3. 2 root 5 divided by 3. And 2 minus 2 root 5 divided by 3. Does that work? 4 times 4 plus 9 times 2 square root of 5 divided by 3 squared. Yeah, it does. Okay, so we need the equation of the tangents. So it's always worth drawing the tangents. So here's a tangent and here's a tangent. Well, if you have a line with gradient, m passing through x0, y0. So if you have a point at x0, y0, and a line passing through, and the gradient of that line is m, then the equation of that line is y minus y0 equals m multiplied by x minus x0. But we know that the gradient is the derivative. So we can modify this to y minus y0 equals the derivative at that point multiplied by x minus x0. So this is the equation of the tangent, and for the normal is going to be the same thing, but it's going to be minus 1 over y prime x0. Type 1 if you understand this equation, please. The last one. Type 0 if you don't understand it. Y prime x0 means the derivative of y at point x0. Y x0 derivative at point x0. Okay. Sorry, I don't know how to pronounce your name. Khosrov. What in particular? Do you have any particular question you don't understand, or did you lose me at the beginning? Any particular part that you'd like explaining? Right. Okay. Right, so we substitute that. So y minus y0, so that's 2 square root of 5 divided by 3 equals the derivative. Now you need to find the derivative, of course. So the derivative, you're going to use the same method. You're going to use 4x squared plus 9y squared prime equals 36 prime. So there's going to be 8x plus, this is going to be 18y y prime equals 0. So y prime is going to be 8x minus 8x over 18y, which is 4 over 9 minus 4x over 9y. So this is going to be minus 4 multiplied by x, which is 2, divided by 9 multiplied by y, which is 2 square root of 5 over 3. And multiplied by x minus x0, so x minus 2. Then you simplify this equation. It's going to be y minus 2 square root of 5 over 3 equals, that's 8. So 2 cancels, 3 cancels, square root of 5. So it's going to be minus 4 square root of 5 divided by 15 multiplied by x minus 2. So this y is going to be equal to, like, honestly, I'm too lazy to, well, okay. All right, I'm not that lazy. Minus 4 square root of 5 over 15 x plus 8 square root of 5 over 15 plus 2 square root of 5 over 3. So I multiply this by 5, so that's 15, so that's 10. So that's going to, so the equation is y equals minus 4 root 5 over 15 x plus 18 root 5 over 15. 18 over 15, we can simplify that by 3. So it's 6. What? Over 5. Oh, 6 over 5. Right. So that's the equation. That's the first one. And the other one is symmetrical. So you can literally say, well, that's the first line, y1, and y2, that's the second line. And it's symmetrical, so it has the opposite gradient. So it's going to be plus 4 root 5 over 15x. And the y-intercept is also going to be the opposite, so minus 6 root 5 over 5. And you can also be very smart about it, or very smug. Depends what you like more. So you can say the equation of the lines are minus plus 4 root 5 over 15x plus minus 6 root 5 over 5. So that means when it is minus, it is plus, and when it's plus, it's minus. So you can put the equations into one. Right, okay, let's move on. The volume of a cylindrical tank increases by 50 square cubic centimeters every minute. The tank has a constant height of 10 centimeters. What is the rate of growth of the constant height of 10 centimeters? What is the rate of growth of the radius when the volume of the tank? Okay, that is a very weird tank. That is a very weird tank. So basically what's going on, we have a tank, which is like this. It has a fixed height of 10 centimeters. But water is added. Water is 50 cubic centimeters per minute. We add water to the tank, and the tank becomes bigger, but it doesn't become taller, it becomes wider. So this is a bizarre tank. So you can imagine how it works. I have different ideas. Maybe the walls are made of rubber, and the squeeze between two surfaces. Maybe it's a rubber balloon, and with the water pouring in and it's increasing in size. I don't know. I don't know what it is, but it's a bizarre tank which becomes bigger as water is added. Okay, becomes wider, but keeps its shape. Right. So what do we do? Well, we need to find the volume of the tank. Volume of the tank is area of the base times height. And the area of the base is pi r squared, and the height is h. Okay. We know that the water is added. This is the rate of the water being added. That's the rate of change of volume. So it's the rate of change of volume, dt. That's 50 centimeters cubed per minute. And what they are asking, they're asking at which rate is the radius increasing. Okay, so what we do is we take the volume and we differentiate it with respect to t. We find dv dt equals d on dt of pi r squared h. Now pi doesn't change, h doesn't change, so we can write d, so we can take them out. So it's pi h d on dt of r squared, but r does change with time, so we can't just take it out. So we need to differentiate it with respect to time. So we use the chain rule here. It's going to be pi h d on dr of r squared multiplied by dr dt. So it's pi h 2r multiplied by dr dt. So in other words, the rate of change of volume is equal to 2 pi r h. Really? Yeah, 2 pi r h multiplied by dr dt. And we need dr dt. So dr dt is equal to 1 over 2 pi r h multiplied by dv on dt. And we know everything. We know that 1 divided by 2 times pi times r. Oh, we need r. So what is r? So from here, 500 equals pi r squared multiplied by h, which is 10. So that's 50. So r is equal to square root of 50 over pi. That's the radius of the tank. We put that in. 2 pi multiplied by square root of 50 over pi, multiplied by h, which is 10, multiplied by the rate of change of volume, which is 50. So you just get a number. It's not going to be pretty, so I'm just going to use my calculator. 50 over, not 50 squared, 50 over 2 pi multiplied by 10 multiplied by square root of 50 over pi. Zero point 0.20 centimeters per minute. That's it. That's the rate of change of volume. Second equation. This one, or which one? 1 over. Oh, I just rearranged. I have dv on dt, and I have dr over dt. So I just divided both sides by 2 pi rh. Okay, 3, 4. Show that the function gy, so we have the function x equals cos 2y plus 3y. We need to show that it is invertible. Invertible. In which case a function is invertible? A function is invertible if it's a one-to-one function. Oh, we have a function. And for example, this function is invertible. Invertible. But this function is not invertible. Invertible. That means it doesn't have an inverse. Only one-to-one functions have an inverse. Only one-to-one functions have an inverse. Inverse. Yeah, are we clear on that? So if a function is a one-to-one function, it has an inverse. If it's a many-to-one function, it doesn't have an inverse. So basically, we need to prove that this is a one-to-one function. Well, we differentiate it. We find the derivative of dx, dy, and that's going to be 2 sine 2y with a minus plus 3. Dx and dy. And we can say, okay, that's fine. What do we know about this? Well, we know that sine can only take values between -1 and 1. So sine 2y can only take values between -1 and 1. We multiply by -2. Multiply by -2. And it's going to be -2 sine 2y. And it's the sign is going to be changed. So -2, 2. And then we add 3. We add 3 and we get 3 So minus 2 sine 2y plus 3 is going to be greater or equal 1 and less than or equal 5. In other words, dx on dy, the derivative of x in respect to y, is greater than 0 for any y. For any value of y, the derivative is positive, and that means it is an increasing function, because if the derivative is positive, that means the gradient is positive, and if the gradient is always positive, the function, and this is a weird function because this is x with respect to y, the derivative is always positive, the gradient is positive, so dx over dy is positive, therefore the gradient is positive. That means it is a 1-to-1 function. Therefore, it has an inverse. Okay. So we've shown that it has an inverse. Then we've shown that it has an inverse, and therefore we can invert it. So we have x is equal to cos 2y, y plus 3y. Oh, they're not asking for the inverse. Is it actually possible? No, I don't think it's possible to find the domain, the inverse itself. I mean, it's a hassle. They're not asking for the inverse. Sorry, they're just asking for the domain, of the inverse. Well, we know that if you have a function, the domain is R. And this function is a constantly increasing function. It's like this. So the range is also R. Range is R. Is all real numbers. Not it's G, sorry. And the inverse function, the domain matches the range of the original function. So it is R. And the range is also all real numbers. Yes, with inverse, the domain of the inverse function the domain of the inverse function is equal to the range of the original function, and the range of the inverse function is equal to the domain of the original function. It's quite straightforward. So not a very sophisticated problem. It's unusual, yeah. Imagine be constantly given, but not containing all real numbers. Yes, of course, it can be, but not in this case. Because we can, okay, let's say we want, well, we can find the limit. We can find the limit of cos 2y plus 3y as y tends to plus infinity. well, we can obviously see that it is plus infinity, because cos 2y is only between -1 and 1, and 3y is infinite. So we have a number between -1 and 1 plus infinity is infinity. And the limit of y as y tends to minus infinity of cos 2y plus 3y is going to be minus infinity, because as y becomes really, really small, and this is a limited function, so it's between -1 and 1, so you can say that, well, that's minus infinity. So the function all takes, and it's a continuous function. That means it takes all the values from minus infinity to infinity. It's continuous between minus infinity to plus infinity. And of course, sketching always helps. And so I'm going to do y equals 2 cos 2x plus 3x. Sorry, cos 2x, not 2 cos 2x. I got scared there for a bit. So you can see it's an increasing function. It's a monotonic function. A monotonic means constantly increasing or constantly decreasing. Sketch the surface, identifying at least 4 level curves. What are the shape of these curves? Okay, so to sketch this, well, we need, well, it is a three-dimensional shape. So what we can do is first sketch the shape for x, y for several different values of z. So let's say z equals 0, z equals 1, z equals 2, z equals 3. 4 different level curves. And it's going to be z equals 0. So that's 0 equals 3 minus x squared minus 2y squared. So that's going to be x squared plus 2y squared equals 3. Oh, that's an ellipse, right? So for x is square root of 3. Square root of 3. Wow. And y is square root of 3 over square root of 2. So that's somewhere here. This is the shape for x equals, so z equals 0. Now z equals 1, so that will become x squared plus 2y squared equals 2. So it's going to be a smaller ellipse. X squared plus 2y squared equals 1. It's even smaller ellipse. And for z equals 3, it's x squared plus 2y squared equals 0. And this is only possible when both x and y are 0, right? If you notice, like x squared plus 2y squared is 0 only if it's a single point, xy equals 0, 0. So it's a single point. All right, 4 level curves. So maybe one more. This is for z equals -1. So z equals 1, z equals 2, z equals 3, z equals 2, z equals 3. Right. So not yet. Not yet. You do in the assignment, you do. But I've just seen what happens when it looks like this. And now you do the z-axis as well. So you do, we tend to draw the y-axis going to the right. The x-axis goes towards us, and the z-axis goes up. This is the standard way of drawing. Okay. And now for different values of z, when z is 0, when z is 0, it is a big ellipse. So for z equals 0, it looks like this. Z equals 0. For z equals 1, it is a smaller ellipse and it's higher up. Z equals 2. Oh, sorry, that's not good. That must be like this. Z equals 2. Z equals 3. And sorry, z equals 3. So it's a shape like this. It's a surface like this, and it goes like this. Okay. Let's draw it on a 3D calculator. So here it is. Here's the shape. Here's the x-axis. Here's the y-axis. There's the z-axis. Well, almost the same thing as I have drawn. Almost as neat, but yeah. Yes, so please draw the z-axis as to the best of your ability. Of course, you can see how I struggled here, but the idea is the thought that counts. Okay. Yeah, so you can add yeah. Now, and look what happens if I add the plane. So if I add the plane, this is z equals 1.5. So this is a plane that cuts our paraboloid, our elliptical paraboloid, like this. And if I change the height, I'm allowed, if I change k, I can move the plane down and up. Right? So I'm cutting, the plane that is doing the cutting changes. So I'm just going to see it from the top. So this is the x, this is the x-axis, and this is the y-axis. The red is x, y is green. So look what happens when I change k. I cut the ellipse, and it becomes bigger, bigger, and bigger. So, yeah, that's fine. If you need to leave, leave. That's fine. So yeah. Okay, and finally, we have problem 6. Find the second order partial derivatives for the following function. First and second order. So the first order derivatives are df on dx and so first order, and df on dy. Second order, we have d squared f dx squared, d squared f on dy squared, d squared f dx dy. And just in case, let's do d squared f dy dx. Let's see if they are the same. So how do you do partial derivatives? For partial derivatives, you just treat the other variable as a constant. Remember, if I do df dx, if I do a derivative with respect to x, I have to use chain rule here. So for the normal derivative, normal derivative, so derivative, that's df on dx. I would do 8 x cubed y prime minus 14y multiplied by y prime plus 2. And this one, this is going to be 3x squared y prime plus x cubed, no, 3x squared y plus x cubed y prime. And multiplied by 8, so it's going to be 24 plus 8. So 24 plus 8. So just move that here. So if you were looking for the derivative, it would be like this. But you're looking for the partial derivative. Partial derivative. A partial derivative is delta f delta x. In here, you treat y as a constant. So it's simply for this one is going to be 8x cubed. And what? No, sorry. Apologies. It's going to be 24 x squared y. We've just treated it as a constant. This is 0 plus 0 plus 2. So partial derivatives, in a way, are much simpler. It's going to be that. So the partial derivative is 24x squared y plus 2. With respect to y, now I treat x as a constant. So it's going to be 8x cubed minus 14y plus 0. That's it. Now the second order, to do this, I do d on dx or of dx, sorry, df dx. So I take the derivative of the derivative. So that's going to be 48xy plus 0. This is going to be d on dy of df dy. Applications of partial derivatives. Everything, literally everything. All the physics, all instances of physics. The most common is the wave equation. The wave equation uses partial derivatives. And then d on dy, so that's the derivative of this. So that is 0 minus 14. So it's minus 14. The second derivative of that. Then df on dx. So it's going to be d on dx of df dy. So we derive df dy, this one, with respect to x. And it turns out that this is going to be 24x squared. And now we find d on dy on df dx. and that is d delta, sorry, delta, not d, of course, delta. D on dy, that's of df dx, so that's 24x squared. Yeah, so they have to be the same. They always are the same. So I've just shown that. Always the same. Always the same. Right, I have to go. So I hope you enjoyed today. Do watch my other webinar if you're still confused. And good luck with the assignment. And hopefully see you back next week. All right, see you. All right.